windows, which I'll start in a minute, multi-pollutant mixtures, and sort of affect heterogeneity. And I work a lot in these areas, and especially trying to combine these together into coherent modeling approaches. So before you go in, just thanks to the team that worked on this with me, the main methodological approaches that I'm going to be talking about were developed by Dan Mork, who's currently doing a postdoc at Biostat, but previously was a PhD student here who I advised. And then Song-Won Im's picking up his work here, and also with Mark Weisskopf, Brent Kuhl at Harvard, and Marianti Cormatulo at Columbia, and Bob and Roz Wright, and Leon and Hugh and Matilda Chu at Mount Sinai. So all their contributions. So air pollution, of course, is bad for us. You guys all know that, both because of what you do, but also from where you live and work. And so I'm going to forego the sort of intro on that and focus more about the more specific area that I'm dealing with and the methods in it. And that's this idea of identifying critical windows of susceptibility. And so those can be sort of loosely defined as periods in time during which an exposure can alter a phenotype. And so by this is what we mean is, for example, it might be that, exposure to fine particulate matter in week 10 could increase, or week 10 of gestation could increase susceptibility to have asthma, increased risk of having asthma in childhood or something like that. So we really want to identify both the time that the exposure affects the outcome, but also on top of that, the exposure response relationship. And to do this, we use data that looks something like in this schematic here. And so in this, each of these lines represents PM 2.5 exposure, averaged over weekly intervals for each of the first 37 weeks of gestation for 4 different mothers. So each line's a different mother. And so what's important here is that at any given time point, we have this between individual variation, but we also have this variation within person over time. And we want to exploit that data structure to identify these critical windows and estimate exposure response relationships. The reason that we do this is that, if we can identify when something's happening, we might be able to get at the mechanism by which it's affecting an outcome. So if we know that exposure during week 10 gestation affects risk of asthma, well, then we can look at what developmental phases are going on at week 10 gestation and try to get at the mechanism by which exposure affects the outcome. So to deal with these type of data, what's often used, or at least more recently has been used quite a lot, is a distributed lag model, or DLM. And on the face of it, a DLM takes a pretty simple structure. We're regressing our outcome Y on repeated measures of an exposure. So we have exposure X at times 1 to big T, which in our examples will be 37. We'll use weekly average exposure during gestation for the first 37 weeks. And then we control for some covariates and confounding variables. And in the linear model, of course, we have our additive error. And so on the face of it, this is just like a simple regression model. But the challenge comes in because our X's, our exposure data, are autocorrelated with each other. And so what's typically done is we fit what's called a constrained distributed lag model, where we constrain these thetas to vary smoothly over time. And this serves 2 purposes. First, it adds stability to the model, so it's just a form of regularization. And so, regularization. And it also conforms with a biological hypothesis that exposure at proximal time points are likely to have similar effects. And so if we don't do this, what we sometimes see is that, the effect in week 1 is positive, the effect in week 2 is negative, the effect in week 3 is positive, and we get this oscillating pattern, which is typical of multi-correlation, collinearity in our models, but also probably not biologically plausible. So we fit this model and we get something that looks like this over here. This is just an example I had around from analysis we did of the access birth cohort based out of Mount Sinai. Boston area birth cohort. And this shows a DLM fit to a group of boys with the outcome was asthma around age 3. And so what we see here is that sort of there's this bump in our estimate. And during this period, our 95% interval doesn't contain 0. And so this is what we'd refer to as a critical window, an area where our interval doesn't contain 0. So essentially what I'm going to talk about is trying to fit models like this and do sort of bump hunting, trying to find where there's an increased association here in it. So why would we do this? Well, there are good reasons to use a distributed lag model. This figure here is from a paper we did 2017, an AJA paper where we looked at distributed lag models compared to using just trimester average exposures or TAEs. And so this shows here for each of these, this dashed red line is a true distributed lag function. So it's those thetas from the previous model that I simulated some data from. And then here, this line, the solid line, is the average estimate across 1,000 replicate data sets, so in a simulation. And so if we look at these, this column here is a distributed lag model, and it does pretty good at approximating the true underlying exposure response function. You notice is if we fit our trimester average exposures, so we put all 3 of those trimester average exposures in a single model, that's what we call the joint TAE model. In this case here, where the true effect occurs only in one window, this model does really well. But when the true effect expands multiple trimesters, so it doesn't conform with sort of clinically defined trimesters, then we get some deviation from the truth. And it's not terrible. We get the general gist of it, right? We know that the second and third trimesters are the most important and the first one's not. But there's clearly some bias involved by misspecifying our breakpoints in this model. And then the sort of scary one, which I think historically has been the most common approach, is to fit 3 separate models, one for each trimester. And here, it doesn't matter if the true effect is constrained to one window. You get something that really doesn't at all reflect the underlying pattern. So in this case, we had erroneously conclude that we had a larger effect in week 1 than in trimester 1 than in trimester 2. Right. And so the DLM does well, and we're proponents of using it because of 2 main things. First, we're simultaneously adjusting for exposure at all time points. So the separate TAE model, it fails because we didn't adjust for exposure in the other trimesters. But it also, in this case, you can see it adapts to find critical windows or distributed lag effects where the structure isn't defined by clinically defined trimesters. And so it's a more data-driven approach that tends to perform better on average. But it's not perfect. And there are a few sort of larger problems with it. It has a tendency to over smooth, at least using current estimation approaches, right? So you can see that a little bit here. For example, this one, it's sort of over smoothing the underlying function. And if we decrease the signal to noise ratio, you just see that all of these get over smoothed even more. There's a lack of DLM methods for mixtures. There's a lack of DLM methods for modification and effect heterogeneity. And so in this talk, what I want to talk about is how can we use Bayesian additive regression trees, or BART, to solve all these problems. And so we found ways to sort of add structure into a BART model, and I'll explain what BART is in the next few slides. And it turns out it creates a really powerful framework to estimate a whole bunch of different distributed lag style models that we can use to solve a lot of different problems. So what is BART? BART's Bayesian additive regression trees. It's a modeling approach that was introduced by Chipman, George, and McCullough in a 2010 Annals of Applied Statistics paper and built off some previous work by them. It's just a really flexible, non-parametric Bayesian model to estimate a general mean function. So outcome y regressed on some function of a vector of predictors plus additive errors. And what's great about BART is it's highly effective. It has state-of-the-art predictive performance. And it also allows for coherent Bayesian inference. So compared to some things, some other sort of black box models or other random forest type models, you get a really nice inference immediately out of this model. More recently, it's been used a few times to try to estimate effects as opposed to prediction. So there's a few groups that are trying to work on causal estimation using BART and other such things. And of course, this talk, since we want to estimate a distributed lag function or exposure effects, we're going to be thinking about estimation, not prediction. So briefly, what these models do is essentially they're the key building block is to find a binary tree. And so this is an example of a binary tree here. We have some data in this example that has two predictors, X1 and X2. And so what happens up here at the top is all the data is grouped together into one group, and then we split it up into two. And so we split it up based on some decision rule. So in this case, it's saying X1 is less than A versus X1 is greater than or equal to A. And then this group of our data that had X1 greater than or equal to A, we further subdivide into multiple groups based on our other covariate X2. And so what this tree is going to do is it's going to divide up the data into different groups, mutually exclusive groups, right? So we could think about this could be, boys with obese mothers, girls with obese mothers, boys with non-obese mothers, girls with non-obese mothers. And then there's an associated mean parameter for each group. So each tree is just defining a really simple function here. That's saying, if we have a predictor X and a tree structure here, this function is going to equal mu B if observation I falls into terminal node B. So each of these trees just defines this very simple function. It's piecewise constant function like this. But the power comes in when we ensemble these trees. So we add multiple of these trees together. And so we can take sort of our regression function is just going to be some of those G functions, each defined by a tree. When we add these together, we're combining these really simple weak learners, these really simple exposure response functions together into an ensemble that can really well approximate a wide class of regression functions. It works great for a number of reasons. It can approximate that wide class of functions, but also by using an ensemble, it's really robust model. We tend to avoid local minimum and get really good predictions. Model fits. So what does this have to do with distributed lag functions? Well, the first concept I want to introduce is this idea of a treed distributed lag model. And so we're going to fit the same distributed lag model we had before, but we're going to add structure to the thetas using a tree. So the key concept here is that we're applying BART to a single variable, and that's time. And we're going to divide up our exposure time into multiple segments. And then within that, each of those segments, there's going to be a constant linear effect of exposure. So here's a little example here. We have a really simple tree. It divides up time based on two breakpoints, T1 and T2. And so we've divided our time span up into these three segments. And then this gray line here, this represents the linear effect of exposure for all time points in here. So theta 1, theta 2, up to theta t sub 1, those are all equal to each other and all set at this value. And then between T1 and T2, there's a larger exposure effect. And then between T2 and the end of our time span, we have a smaller effect. So we're using trees to define a really simple piecewise constant distributed lag model. And in doing this, what we're doing is we're learning from the data what this tree structure should be and what the terminal node effects are. And so that means that we're learning where these breakpoints are and what the effect within each of these breakpoints is from the data. So we can have a tree that doesn't split at all and there's just a constant effect. We can have a tree that splits many times and has an effect that jumps around a lot. Just like with other BART models, we're going to use an ensemble of trees. So we'll use capital A trees. In all of our models, we use 20. It works really well around there. We don't gain much from going bigger. Using this ensemble, it adds robustness, but it also allows us to approximate smooth distributed like functions. And so we can approximate these functions by having sort of each tree has a slightly staggered breakpoint. So when we combine those, then we can get this thing that has very little small steps. And so we get a stepwise function that approximates smooth functions very well. So you can sort of see a schematic here where maybe we have a tree that divides into 4 groups and 1 and 3, and then one that doesn't divide at all. And to get the overall distributed lag effect, we're just summing across trees. So the theta 1 would be this number plus this number plus this number plus this number. We're just adding across. Yes. Right. And so all of these trees, again, are just learned their structure and those effects from the data. So here's a sort of schematic of that. This red line is just a distributed lag function that I simulated, right? So at 0 for a ways, and then it sort of has this hump and then goes back to 0. So I fit our model here to it with 20 trees. And so each of these lines represents the estimate from one tree, or the contribution from one tree. And what's, I guess, obvious to me here is that all these trees fit the data terribly, right? None of these are anywhere near what the red line is, right? We have this one here that starts down as a negative effect and then jumps up to a large positive effect. So it's just a piecewise constant with 2 pieces, right? We have a few others that bounce around. A whole bunch are just centered on 0 and not breaking at all and not really doing much. But when we ensemble these, when we add these together, what we get is this line here. And this tends to looks pretty good. We're now approximating our function pretty well. And then if we do this over 1,000 MCMC iterations and take our posterior distribution, that does really well. We get this nice distributed lag function over here, where this black line is the posterior mean, and then these gray lines are posterior intervals. So we take these weak learners, these trees that don't fit well, each one's giving a part of that linear effect at a certain time point. Add them together, we do better. Estimate this full posterior, and we do really well.
Andrew, a quick question on that figure in the 20 trees. Those are not it's not 20 proposed trees. Those are after sort of the acceptance of the MCMC of maybe many trees.
Yeah, this is actually just the last iteration I ripped off of a run.
Okay.
So it's fully converged. It looks like, yeah.
One iteration getting the sort of initial trees that were accepted.
Say that again?
For the 20 trees for the initial MCMC iteration, those are the 20 trees that were sort of accepted.
Yep, these are the final ones, right? So they change each iteration, but this is what they looked like at that one cross section at the end.
Okay, that's why they do fit the data somewhat, but not
perfectly. Yeah.
Okay.
Right. Yeah. I will say you can, if you make some true underlying exposure response function or distributed lag function. So if this was just piecewise flat here, jumped up and was flat here, went back to 0, you can fit it with one tree. And sometimes your posterior looks like that, where you have one tree that's just perfectly fitting the data and all the other trees are doing nothing, which is kind of interesting. So I guess the obvious question is why go through all this trouble, right? We have a nice distributed lag framework with natural splines, our penalized splines, our Gaussian processes, principal components. People have proposed all different things. They generally work pretty well. why bother with all the fuss about this treed model? And there are a few reasons for that. The first reason is that I think it does work better, or at least can adapt to more underlying distributed lag functions. So here you see a few examples. On the left, this is what we call a hard critical window. So it's flat, there's no effect, and then it jumps up. In this window, there's a constant effect, and then it jumps back to 0. Here we use a penalized spline model, and a few things jump out. First is that it, of course, does get the general idea. It does get that the largest effect is here. But when it goes back down, it over smooths this hard function. That makes sense. A spline shouldn't be able to approximate a piecewise constant function. But it extends this critical windows a few weeks on either side. So we're estimating a larger critical window than is truly there. And then there's this rebound effect as well, where we get this sort of a significant effect in the opposite direction. And that's always a little confusing, and how to interpret that, and how to present that in the papers as well. And this is something that even in, that we notice in a lot of settings, that we'll get these sort of rebounds and wobbling outside of it. Our treed model does a really good job of approximating it, right? It's not perfect. There's some error, of course. But it defines the window really well and adapts to this piecewise constant shape. But it can also adapt to smooth functions here. So when we have a critical window with a nice smooth exposure effect, the spline model does a lot better. It still extends the window a tiny bit. But our treed model can really adapt to that very well and do it. So it can adapt to a wide variety of functions. The other reason is because this extends really nicely to mixtures. And that was our real motivation behind doing this, is to develop a mixture model. I might just pause there and see if there are any questions before I jump into mixtures. Is there any? Yeah, okay, that's a good question in the chat from Sandy. So, right. It does a pretty good job of detecting small effects. The big thing we notice is the difference between, so she asked about non-parametric models are often data hungry. Is the BART-based approach feasible for detecting small magnitude effects? It does pretty well. The difference is that it's a shrinkage estimator. So we do find that sometimes we're shrinking the effects too much. So we get the right idea, but we don't get that like significance that we want to highlight in our abstract. And so we lose more from this sort of shrinkage priors we're putting on the effects at each time point. I will say that we're currently doing sort of a follow-up analysis to using that access cohort where we have 200 observations. We have a mixture of 8 components, and we've applied our tree model. And so this model has like 100,000 parameters in it or something with n equals 2. And we aren't getting strong results with this method, but we're definitely picking up a signal. So we're understanding there's something there that we can replicate with other methods or simpler one pollutant models. So it does do a good job of picking up these effects, but it doesn't get it, it shrinks it a little too much at times. So how about critical windows with mixtures, right? So there are a lot of challenges when we think about critical windows with mixtures. This is a data setting where we have multiple components of a mixture. So this little schematic, not the data I use, is metals. And then each column here represents an individual. And so for each of these components, we have repeated measures of their exposure. And so this turns out to be a high dimensional exposure space once we multiply our number of components times the number of time points. We also get a complex correlation structure. So there's high correlation between mixture components at each time point. That's of course what we see in all of our mixture analyses, even if we don't have repeated measures. But then we also have high autocorrelation among the repeated measures of each component. So we get this complex correlation structure. And then we also have often have a very high dimensional parameter space as well. We want nonlinear associations often. We want interactions, and particularly time-sensitive interactions. And by that, I mean that would be exposure at time to one component at time point 1, maybe changes our susceptibility to a second component at time point 10 or something like that. So it's sort of this priming hypothesis that exposure to one thing at one time point can make you more or less susceptible to exposure to something at a later time point. So there are 5 approaches to do this that I'm aware of. The first one is Bayesian kernel machine regression distributed lag models. And that's something I developed with the Mount Sinai group and Bright Cool. And this takes our BKMR model, Gaussian process regression, and sort of tailors it to have these repeated measures of exposure. This is the model that has all the bells and whistles, does our nonlinear associations, it does interactions, it does higher order interactions and time-sensitive interactions. But we pay a price for that, right? If we fit this super flexible model, that gives us higher variance estimates. And so it's often hard to learn much from the data. We're asking a lot from our data. And I know a lot of you guys have used BKMR before, and using the current computational approaches, it's a computationally intensive model to fit. And so it's not feasible to fit for very large sample sizes using the current approach. I should say these models are arranged from most flexible to least flexible. The next one is the tree distributed lag mixture model, which I'll talk about today here. There's a related model by Joey Antonelli at Florida, which uses a spline-based model with component selection that really focuses on how to choose your priors to avoid false positives, avoid including a component that shouldn't be included in our mixture. Josh Warren and Howard Chang are working on an approach called critical window variable selection for mixtures. So this builds off some work they did for just sort of avoiding the over smoothing problem in DLMs that they've done with some Bayesian hierarchical modeling. Uses Bayesian variable selection approaches to select time points where there's an effect. This model allows for main effects and interactions at a common time point, but not the time-sensitive interactions. And it also makes some sort of assumptions on the direction of the effects. So the effects are constrained to go in the same direction, which is a pretty strict effect. And then Chris Jennings' team has developed lag-weighted quantile sums, which also makes some very strong assumptions that the exposure effect always needs to go in the same direction for all of our components there. So I think this tree distributed lag mixture model is sort of the best compromise between these methods. It allows for these time-sensitive interactions. We can include quadratic main effects if we want a little bit of nonlinearity, but it's computationally scalable. So we can fit this on large data sets. We can fit this with a large number of predictors, and it tends to have really good properties. So what we're trying to fit is this model here, which we call the distributed lag mixture model. And so again, this is just linear regression, but it's high dimensional linear regression now. And so what we're assuming is that we have capital M components in our mixture, each a set capital T time points. So theta MT is the effect of exposure at time M, or sorry, of component M at time T on the outcome. And then we have these theta M1, M2, T1, T2, which is the effect of exposure at time point, or for component M1 at time point T1, and the interaction with exposure M2 at time point T2. So we're really estimating this full sort of interaction surface. So for each pair of chemicals, we have a capital T times capital T surface of parameters we're estimating. So this includes time-sensitive interactions. We can do interactions, self-interactions to get that quadratic main effect or sort of two-hit hypothesis. And so the challenges here are that this is a big model, right? So we have M times T, M plus 1, choose 2 T squared parameters, and this grows quickly in both M and T. So also a data example later where we have 5 components, 37 time points, and so that gives us 20,000 parameters. So that's a big model already. Especially if we want to think about fitting this on birth cohorts that aren't huge. The other challenge is that we need to come up with a nice way to add structure to all of these parameters here to regularize our model. And that's where the trees come in, building off that sort of basic tree distributed lag model approach. So when we're thinking about mixtures, the key building block to our model is going to be tree pairs. Okay. And so a tree pair looks something like this. And it has two regression trees in it. This is the exact same picture I showed you before. It's this simple regression tree that divides up the time span into 3 groups. And so this here is going to be our main effect distributed lag function for one exposure, M1. It's a pair, so we have 2 of them. So we have another tree here. This one divided a time span up into 4 groups. And this is the tree for the main effect of exposure M2. So we have 2 exposures. Each one gets a tree to divide up its main effect into 4 groups. And then there's that constant linear effect of exposure during each of these time spans. What we're adding in here is this idea that there's an interaction between these 2 trees. And that's represented by this surface here. And so what we're really doing is we're taking the interaction between each of these 3 time segments and each of these 4 time segments to get this full interaction surface. So you could think about this axis here being enumerated theta1, theta2, theta3 across our time span. And so here, this is representing the linear effect of multiplicative interaction for all exposures for M1 over this time span and M2 over this time span in here. So we get this very simple piecewise constant interactions. And so this is like the building block of what we're doing. You can think about these as sort of these objects that have provide some sort of structure and some sort of effects for us. And I think this is really cool because I don't know of any other model that's used trees that interact like this. Usually we're just thinking about ensembles of trees where we add them together. And here we're using these 2 pairs of trees, an ensemble of pairs of trees, where each of those pairs has 2 trees that interact with each other, which is pretty cool. So I already told you that these tree structures we're going to learn from the data. We'll just estimate those with an MCMC algorithm. And then these exposure effects, including the interaction ones, we're also just going to estimate using pretty standard Gibbs sampling approaches. But the question is, what is M1 and M2? Right? There are different ways to think about this. We could pre-populate these structures. And so if we have 3 components, PM, NO2, and temperature, we could have a tree pair for PM and NO2, a tree pair for PM and temperature, and a tree pair for NO2 and temperature if we wanted, and just pre-populate them. But that doesn't scale well when we have multiple mixtures. And it's pretty rigid also as a framework because we have to predetermine how many trees would apply to each pair, and it doesn't adapt to what the signal in the data. And so what we do is we actually estimate the exposures that are assigned to this tree pair. And so essentially you can think about us as having an MCMC algorithm where we have these tree pair structures. So we have this tree here, all these effects. And maybe that's applied to PM and temperature. And we're going to have a proposal that says, actually, let's try replacing temperature with NO2. And we're going to see how this tree fits with when these exact tree structures, these exact effects are, instead of looking at the interaction between PM and temperature, looks at the interaction between PM and NO2. And so this can be done with just a simple Metropolis-Hastings approach, where we propose these switch exposure steps, we call them, to apply these tree structures to different combinations of exposures. So this is just saying that in math here, that sort of Sij equals M if tree J in pair A is applied to exposure M, and we put a prior on that. Right? We add to the BART algorithm this new step, this switch exposure step. And this has some nice advantages. What happens here is it's possible that no tree uses exposure M. And so if we don't apply one of these tree pairs, or a certain exposure to any of the tree pairs, then that exposure is selected out of the model. So we have this really nice form of component selection. It also enforces hierarchical variable selection, by which I mean that if we have an interaction in the model, we must have both main effects in the model as well. So we don't get this weird situation that a lot of Bayesian or older, more traditional Bayesian variable selection approaches fall into, where you get an interaction effect, but no main effect. We always get those main effects, which we like. It also gives us really nice inference on the which components are included in the model. So we can get a proper Bayes factor out of this model for each of our components being included in the model. So we tested this out in some simulations. And I'll show you two of them. This first one is for a single pollutant model. So we're really actually testing out the tree distributed lag model to see how that does. So in this case, we used a binary outcome with a single exposure. And we chose binary because some of the competing methods only had code available for a binary outcome. We used a sample size of 5,000, and we tried two probabilities of success. So 0.5, which is our easier setting, and then our rare outcome setting, 0.05, which is a harder one to estimate. Our distributed lag function looked like this dashed red line here. So it's sort of that hard critical window I talked about. So it's 0 except for one randomly placed 8-week critical window. I will say we also replicated this with a smooth distributed lag function, and the results were very similar. So we're not just getting our results based on the assumption of this hard window. And then we compared several models. We compared our tree distributed lag model with a single exposure, a penalized cubic spline regression model using Antonio Gasparini's package. This is the first critical window variable selection by Josh Warren. So he's already developed this one for a single exposure. Basically, it's doing Bayesian variable selection across the weeks of time to try to select out periods of time, set them to 0, and then estimate an effect only in those not set to 0. So it's trying to adapt to this sort of hard critical window function. I guess I skipped. We did use real Colorado PM 2.5 data. So we had realistic autocorrelations in our data here. But we also wanted to test out our mixture model as well compared to these single pollutant models. So we also included the tree distributed lag mixture model in here with 4 additional components: NO2, SO2, CO, and temperature. So the first 3 models were fit only to the single predictor PM. And then the last one was fit to the 5 predictors. So overall, our methods did really well. So you can see here they had better distributed lag function estimation, and that's this plot here. This shows the pointwise RMSE across the distributed lag function. This one here with the lowest RMSE, that's the tree distributed lag model for a single component. Has slightly lower RMSE than our penalized spline model, as well as lower than the critical window variable selection model. What was most shocking to us though here is that this one here, to the right, that's the mixture model. And that did almost as well as our single pollutant model. And this was quite surprising because you remember we're fitting this to 5,000 observations, and this model has 20,000 parameters in it. So we're talking about a P much bigger than N here issue. And so our model tends to have really good selection and shrinkage properties, which gives us a very small loss when we fit a mixture model, but there isn't actually a mixture. There's only one exposure associated with the outcome. These two on the right show us about our how well we do at identifying critical windows. So this is the true positive. That's really saying what proportion of the time points we said are in a critical window are actually in a critical window. Is there actually a non-null exposure effect? The false positive is saying, how often did we say there was a critical window when true exposure effect was 0? It wasn't in the window. So all the methods in our simulation did pretty well identifying the critical windows. But what we notice here is that the spline method tends to identify false windows much more frequently than the other methods. And so about 20% of the time points we say are in a critical window don't belong in a critical window with a spline. Whereas the critical window variable selection that's more tailored to our selecting time did better, and our tree approach did really well. It has a much lower false identification rate. And this is sort of a common theme that we have throughout all of our models, that the selection shrinkage properties do really well. So maybe we sometimes lose power to detect windows, but we have an incredibly low false window detection rate. And so we can be much more confident. They're sort of windows that we can believe in, essentially. We also tested this out with a mixture of 5 components where there was multiple main effects and an interaction. At the time we were doing this, none of the other methods were out, so we didn't have a comparison point. But I'll briefly summarize them here. Overall it looked really good. We had what we thought was acceptable RMSE. That's always hard to judge when you don't have a comparison. We had proper 95% coverage on our intervals throughout. We had high precision in identifying the windows, especially because we had a very low false window detection rate. And then we had a high rate of selecting the correct components. That occurred with very high probability. We had a lower rate, not exceptionally low, but lower rate of selecting incorrect components. And generally when they were selected in, their effects were shrunk down. That's why we're not getting a high false selection rate. So we fit this to some data. We're using Colorado administrative birth cohort data. We had 195,000 births. The outcome was birth weight for gestational age z-score, which is adjusted for sex and gestational age, using the Fenton growth charts. We had 5 exposures assessed weekly during pregnancy: PM 2.5, NO2, SO2, CO, and temperature. We controlled for a fairly standard set of covariates. We only have the mixture data for right around Denver, so our analysis was limited to just Denver metro area births. So here are the results from it. I think I'll just explain the results and then talk about how to interpret them a little more in a bit. But what jumps out most of all is this temperature effect. We found that increased temperature was associated with decreased birth weight, especially in the later part of gestation. We also found a slight critical window for SO2 and a slightly larger one for PM 2.5 here. Both increased exposure was associated with lower outcomes. When we're thinking about interactions, there are a lot of different ways to define that, right? Our first regression class, we probably learned that it's, we can think about main effects as being the effect when all other exposures are held at 0. That's not too ideal because we never have 0 exposure. So often people do this as the main effect when everything else is fixed at the mean or the median. What we did here is we tried to adjust for the correlation structure between exposures. So each of these here is really showing the change in outcome, the difference in outcome associated with an IQR change in one exposure. So an IQR change in temperature, and the expected co-changes in our other exposures. So what that means is we're modeling here using a separate model, sort of what the expected value of each of these components is at the 75th percentile temperature, what the expected value is at the 25th percentile of each exposure, and we're comparing sort of that 75% percentile temperature and expected levels of co-exposure compared to 25th percentile of it. So it's sort of a crude approach to try to account for these correlations and not interpret too far outside of the bounds of our data. We did pick up an interaction, which was exciting. So here, this shows the interaction surface between PM 2.5 and temperature. And so these red dots, they show areas where our credible intervals didn't contain 0. So what we see here is exposure to PM at week 20. That's associated. There's an interaction between that and temperature at week 20. But there's also an interaction between exposure to PM 2.5 at week 20 and temperature at week 30. So we get this sort of time-sensitive interaction here, right? And so that's kind of cool to get that there, the sort of priming idea. I will note that these effects are super, super tiny here, so we shouldn't read too much into those. But it is nice to know that we are able to pick those up there. This also just shows the distributed lag function estimated for temperature on the bottom when our when co-exposures are all fixed at a certain percentile, the 10th, 25th. So we see that sort of increased effective temperature as all of our co-exposures move to higher levels there. Might take a break there. Any questions on the mixture approach?
Andrew, I have a question about maybe what you mean by mixture approach or mixture effect. And maybe if you go back to the last slide. So what you're fitting is a model with multiple exposures and sort of conditional effects that you get out, right? At each time point across and with the distributed lag model. You're using this sort of potential outcomes kind of risk difference approach for each effect. But you could do that over the entire mixture, right? Of going from all effects that are low to high and get a single risk difference. That would be a mixture effect. Or what do you, is there a...
Yeah, you could make those contrasts if you wanted, right? You could just compare the expected outcome for sort of one distribution of exposures compared to a different distribution of exposures, right? You could plug in our climate simulations and say, what's the expected distribution of birth weights in our current climate versus this future climate or something like that, if that's what you're getting at.
And a single mixture effect of, yeah, or something along those lines.
I think you can. I think some people might object to that. The people who are really trying to build models, the weighted quantile sum type models that have a parameter that represents our total mixture effect. So I think you could do that, although some people might disagree with that statement.
Okay, well, thank you for clarifying.
Andrew, I had a question again too, sorry. I was trying to understand the paired trees, and maybe could you explain to me how a paired tree with like one tree per M, how is that different from a single tree that had two M's in it?
Oh, yeah, sure. So if we had a single tree, right, we would be forcing both components to have the exact same breakpoints between them. And so this gives us more flexibility where we can have one exposure that maybe has constant effect throughout pregnancy, but another exposure that only has an effect in the later part of pregnancy or something like that. So it gives us extra flexibility to allow the main effects to be different.
Okay, thank you.
Yeah.
And this is Duncan. Temperature effects are often U-shaped. What you're showing us here is the a linear slope for temperature at the different gestations.
Yes, it is. I should say we for this model, we excluded the self interaction. So we're restricting the model a priori to have only linear main effects. We did fit it both ways. The results are nearly identical there. But being a quadratic effect, we only have so much flexibility to identify those nonlinear ones, even if we include that. So that's certainly a limitation there.
Okay.
I will say that I'm not going to talk about this today. We also have a tree approach for distributed lag nonlinear models. And so there we pick up a really strong, in the same data, nonlinear effect of PM 2.5, where most of the effect is at lower exposure values there, and there's much less of an effect at higher ones. So I think there's potential to work that into this framework, but not currently done.
Hey, Andrew, this is you. I have a question on your slide 19 about the exposure selection approach. You say if no tree use exposure M, then this exposure will be selected out. But if the exposure are very correlated, do you think the tree will just randomly use one exposure and kick out another exposure? So if that's the case, how you justify the selection?
Yeah, that's a good question. I don't think that'll happen. I think you'll get some maybe confusion between your effects there and not be able to attribute any sort of effect with high probability to one component or the other, but I suspect they'll both be included in the model with high probability. So sort of the opposite. They'll all be included in the model and the effect will be divided up among them.
Okay, so he will perform like a hierarchical selection style.
Yeah, and I think that's because, as I didn't talk about this, but on the linear effects within for each terminal node, we put fairly strong shrinkage priors on those. It's like a horseshoe type prior on them. So we get nice shrinkage properties that sort of avoid that problem, and we'll include both of them in the model.
Okay, thank you.
Yeah. I will say, just like any other of these mixture models, there's a breaking point, right? You can put in super correlated things, whether that's super correlated over time or between components, and at some point, we can't win.
Mm-hmm.
Yeah. Yui?
Oh, I just asked my question. Sorry.
Oh, sorry.
I lowered my hand.
Hand just moved up again. Okay, so I know we're running short on time. This section is quite a bit shorter, but the other thing we want to do is heterogeneity and modification of critical windows. So this is sort of gets at this increased focus on vulnerable populations or precision environmental health. And so the standard approach has been just to stratify the model here. And so there's one approach we came out with, Bayesian distributed-like interaction models, that does this for a single categorical factor, but that's not too satisfying. We'd like to be able to work on a continuous modification or multiple modifiers. And so we've also developed a tree approach for that. I'm going to skip this one for the sake of time. But our heterogeneous distributed-like model looks just like this. And so now we're back to talking about a single predictor, only one exposure, single pollutant. And we just have this theta t is now a function of our modifying variables here. So this means for each unique combination of modifying factors, we'll get a unique distributed lag effect. So the key idea here is we're applying a regression tree to divide up our modifier space, so to make subgroups of our population based on our modifiers. And then each terminal node, instead of just a single parameter, mu, it gets something that looks like a vector that looks like a distributed lag function here. And so this allows for multiple modifiers, interactions between modifiers, categorical, ordinal, continuous variables, all of that. And so just like before, every other BART model, we're doing an ensemble of trees. So we have a whole bunch of modifier trees. And so if an individual is on each of these red terminal nodes, you know that each tree contributes a different sort of part of that distributed lag function, and we sum them up. And we get our total estimate. And so the question here is, this top part is just standard BART. The bottom part is the novelty. And the question is, how do we fit this distributed lag function down here, right? These are just draws from a Gaussian process. We could do that. We could do splines. But you've probably caught on that I really like regression trees. And so our approach is to do more regression trees. And this turns into a cool approach too, because we're fitting this big regression tree, which is dividing up our population based on our modifying factors. Each terminal node, instead of just getting a leaf there that's a single parameter, we're actually just putting another tree on it. So we have trees of trees here. And we have sort of two approaches, a nested tree model, and the shared tree model. The shared tree model, all these terminals get the same structure of their tree. It's computationally simpler, but different effects within each point. Oh, and we're out of time. Should I cut it off?
Maybe 2 more minutes. Just
2 more minutes. Cool. I'm going to give you the. So we did a simulation and it looked pretty well. Worked pretty well. And we applied this to the same data, but this time over all the Front Range of Colorado. So this is where everyone lives, the urbanized area, and it's out of the mountains, so we can actually get exposure data for it. So if we fit just a single model, no heterogeneity to our data, we get a distributed lag function that looks like this. We get this suggestive sliver of an effect in early pregnancy and a small critical window in late pregnancy. This is 2.5 and birth weight again. But when we fit our heterogeneous one, we find a few factors that modify. So this shows everything we included in the model. Checkmark said they're a potential modifier. And the highlights say that maternal age at conception, maternal BMI, maternal education, and maternal Hispanic designation were all potential modifiers. They were included in our model a lot. Here's an example of our inference here. We get, this shows the estimated DLM stratified by BMI and Hispanic status. And so for the Hispanics, we really get no evidence of an effect. And then for the non-Hispanics, we get, for the low BMI group, we could get a suggestive effect in early pregnancy, but much larger effects, and that late window, late pregnancy effect jumps in for the high BMI group there. And so we can look at this by other factors. Each line color shows maternal age in here. And this is pretty exciting here. We see some additional variation by maternal age, but if you think about this, is a four-way interaction between maternal age, Hispanic, BMI, and PM. And so it's a really flexible model where we can get these higher order interactions for modifications that still get distributed lag estimates out of it. I think we can interpret these here, look at the breakpoints in the tree to see if there are certain sort of boundaries where all of a sudden the effect kicks in. So this shows us the most common breakpoint for age was 28 or whatever there. So if we wanted to follow up with the stratified model, we could. So yeah, that does it. I'll just put in a plug that Dan Mork, whose thesis this was, has for these treed models a really excellent R package that can fit all these models and visualize the results and stuff, and super computationally efficient there. And these are the two main papers it's based on. So sorry to run a little late, but thanks for hanging in there. Those of you who were here.
That was great. Thank you, Andrew. Any last questions? I think it looks like people are heading out, but thank you very much. I have some questions, but we'll meet tomorrow morning, so I will pepper you with questions then.
Cool.
So, cool. Great. Thank you very much, and thank you all for coming.
Yeah, thank you, everyone.
You're good with, next meeting, he's good.
Yeah, Andrew's until 1:30, so
Okay,
you will break.
there, good.
Sounds good.
You're good. Okay. All right. Thank you very much.
Thank you.